Well, students, so far we have learnt polynomial interpolations. In this lecture, we will learn how to do error analysis for polynomial interpolations. Let us first get an idea of what is meant by the error in polynomial interpolation and what are they. Let f of x be a given function defined on an interval ab, and let us assume that we have constructed the polynomial interpolation for the function f at some given n plus 1 nodes x0, x1 up to xn in our interval AB. Now the question is, how good is this polynomial when compared to the function f at each point x in the interval I? This question leads to the analysis of interpolation error. Let us make this point more precise. We are given a function f that it needs to be approximated by a polynomial denoted by Pn of x, and this polynomial is an interpolating polynomial for the data xi f of xi for I equal to 0, 1, 2 up to n. So at this level, we can anticipate error involved in the number Pn of x when compared to the number f of x for each x, right? And there is one more level of error that we will come across. We will get this error precisely when we go to compute this interpolating polynomial on a computer, because generally computers will not take the numbers that we give in their exact value. They always round the numbers and take an approximate value of that number. We know this from one of our previous chapters. Therefore, when we give the numbers xi and f of xi to a computer, the computer actually takes it in an approximate form, which we will denote by fl of xi and fl of f of xi. These are the floating point approximations of the respective numbers. For the sake of simplicity, we will always assume that the computer assumes the nodes exactly, but they only commit error in the function values. This is only for the sake of making our analysis simple, but actually we should consider error in both nodes as well as function values. But we study the error analysis in the simplest form. So you assume that your computer is taking your data as xi, fl of f of xi. Thereby, your computer will obviously not find the polynomial Pn of x that you are intended to get, but it gives another polynomial because your data set is fundamentally different, right? Let us denote the polynomial that comes out of this data set as P tilde n of x. Error in polynomial interpolation therefore involves two parts, namely the error in Pn of x when compared to the exact value f of x, which we will call as the mathematical error. And as we can see, this error depends on the variable x. Therefore, we will use the notation me of x. And since this is the error involved in the nth degree polynomial, therefore we will also use the suffix n in the notation. Therefore, the mathematical error involved in the nth degree polynomial Pn when compared to f of x is denoted by men of x. And similarly, we will also define another type of error, which is called the arithmetic error. And this is the error involved in Pn tilde of x when compared to Pn of x. And we use the notation for the arithmetic error as Aen of x. Now you see, I want to have the value f of x, but somehow I prefer to go for an approximate value of this. So I gave a data set to my computer, thinking that it will give me this polynomial Pn of x, but the computer gave me this polynomial Pn tilde of x. Therefore, what is the total error involved in this process? It is f of x minus Pn tilde of x, right? So we will define this total error as basically f of x minus Pn tilde of x, which is after adding and subtracting Pn of x, it can be mathematical error plus arithmetic error, and that in the notation given by Men of x plus Aen of x, because f of x minus Pn tilde of x is equal to f of x. I'm subtracting Pn of x, and that gives me the mathematical error, plus I'm adding Pn of x minus we already have Pn tilde of x, right? Therefore, the total error is nothing but the mathematical error plus the arithmetic error. Let us first consider the mathematical error and try to obtain an expression for the mathematical error. Let us state it in the form of a theorem called mathematical error in interpolation. Assume that f is a Cn plus 1 function on the interval AB, that is, f is continuously differentiable up to order n plus 1, and all the nodes x0, x1 up to xn lie in the interval a comma b where f is defined, and we have constructed the interpolating polynomial of f at these given nodes. Remember, at the mathematical error level, we have no rounding error. There is no floating point error involved in our computation. All the computations are carried over with infinite precision. Then for every x in I, we can find a xi x in the interval AB such that the mathematical error Men of x is given by the n plus first derivative of f at this unknown point xi x. Why this suffix x for the xi? Because this number depends on the variable x. That is why we have denoted it by xi of x. So f n plus 1 is evaluated at this point divided by n plus 1 factorial into the product of x minus xi into x minus x naught, x minus x1 up to x minus xn. So that is what is this notation. This capital pi stands for product. That's a standard notation. Let us see how to prove this theorem. The proof of the theorem is not something new to us. Right from the Taylor expansion proof, we are doing this. I think at least twice we have used this idea in our course so far, but still we will repeat it here. First, observe that if x is one of the nodes, then what happens? See, you take this x as one of the nodes, say xi, then what is Pn of xi? By interpolation condition, this is precisely equal to f of xi, right? Therefore, the mathematical error, which is nothing but f of x minus Pn of x, should be equal to 0 in this case, right? Then mathematical error in xi should be equal to 0. Let us see whether our proposed formula also gives the same value. Yes, surely it will give, because here you have product, and whatever may be your node, that is whatever may be your I, it will be 1 among the 0 to n, right? Therefore, that term will become 0, and therefore this entire term will vanish if x that you choose happens to be one of the nodes. Therefore, the proposed expression for the mathematical error well respects the reality when x happens to be a node. So we will assume that x is not equal to any of the nodes that we have used in constructing the interpolating polynomial. Now in this case, we have something to prove which is non-trivial. Let us see how to go ahead. As I told, the idea is something which we have always used in many places. That is, define a function psi of t, which is equal to f of t minus pn of t minus lambda times phi I equal to 0 to n t minus xi. What is lambda? Well, we have to choose this lambda in such a way that psi of x is equal to 0. Now you would have understood that this idea is quite familiar to us. When you impose the condition that psi of x is equal to 0, that immediately fixes the expression for lambda like this. And you can observe that psi of xi equal to 0 for all the nodes, that is for all I equal to 0, 1, 2 up to n, right? Therefore, how many zeros are there for psi? You have n plus 1 plus this x. So there are n plus 2 zeros for xi, right? What is the next step? Well, you go on applying Rolle's theorem. Let us first apply the Rolle's theorem to psi dash. You have psi has n plus 2 distinct zeros. Therefore, psi dash will have at least n plus 1 distinct zeros in the interval AB, right? And again, apply Rolle's theorem. We can see that psi double dash will have at least n distinct zeros in A, comma B. And in this way, you can continue and see that the n plus first derivative of the function psi will have at least 1 0 in the interval A, comma B. Let us denote that 0 by psi of x. Note that we don't know how this psi of x will look like, but surely the Rolle's theorem gives us guarantee that such a psi x exists, that's all. So in that way, psi x remains unknown to us. We only know the existence of such a point, otherwise we don't know how to compute it. Okay, now let us go to our expression for psi of t and explicitly compute the n plus first derivative of psi. So psi n plus 1 is f n plus 1, and what is the n plus first derivative of pn? And that will be equal to 0. And what is this n plus first derivative? That is going to be n plus 1 factorial, right? Now what you do is you put all this into the expression of psi n plus 1 and put t equal to psi x. You will see that psi n plus 1 of psi x is equal to f n plus 1 of psi x minus lambda times n plus 1 factorial. And since psi x is a 0 of psi n plus 1, you can also see that psi n plus 1 of psi x is equal to 0, right? And that immediately gives you the expression for the mathematical error. Now, how will you get this? Well, you can go back and see how your lambda is defined. Lambda is defined as f of x minus pn of x. That is your mathematical error at the point x. And that lambda is actually sitting here, right? Therefore, this is nothing but fn plus 1 of psi x minus, you have this mathematical error in x divided by the product I equal to 0 to n x minus xi, right? I'm just putting the expression for lambda, that is what is sitting here, into n plus 1. Now from here, you keep n of x on the left hand side and take everybody else on the right hand side. You will see that the mathematical error expression is precisely what we want to show here. So that completes the proof of the mathematical error in polynomial interpolation. Although we got a nice expression for the mathematical error, unfortunately, it cannot be used to precisely obtain the value of the mathematical error at any given point x. This is mainly because of this unknown point involved in the expression. However, if we know some extra information, like if we know the n plus first derivative of f, for instance, if we know an upper bound of the n plus first derivative of f in the interval ab, then we can try to get an upper bound for the mathematical error, right? In other words, if we know this extra information, then we can hope to get an estimate for the mathematical error. You should recall that we have done such estimates for truncation error in Taylor's formula also. To obtain an estimate for the mathematical error, we need a tool called infinite norm of a given function. Let us first define the infinite norm or maximum norm of a given function. Assume that f is continuous on a closed and bounded interval ab, then the infinite norm of f, denoted by this symbol, is defined as the maximum of all x in I of mod f of x. Let us see an example of how to estimate the mathematical error involved in a polynomial interpolation. For the sake of simplicity, let us stick with the data set consisting of only two distinct nodes, x0 and x1, and we are also given the corresponding function values at these nodes. Then we know that the linear polynomial p1 of x is given by f of x0, that is the 0th order divided difference, plus f of x0 x1, the first order divided difference, times x minus x0. Here I am writing this polynomial interpolation in the Newton's form. From our expression for the mathematical error involved in p1 of x when compared to f of x is given by this expression. Now take the modulus on both sides, we get this. Now this can be written as mod x minus x0 into mod x minus x1 divided by 2 into mod f double dash of xi x, right? This is unknown. So what we can do is we can replace this by the infinite norm of f double dash taken on the interval I. Thereby, we will get less than or equal to instead of equal sign here, right? So that is what I am doing. Mod me1 of x is less than or equal to modulus of x minus x0 into x minus x1 divided by 2. Now I am replacing mod f double dash of xi x by its infinite norm. Thereby, we don't care what this unknown is. We just eliminated that unknown by dominating this term by the maximum norm or infinite norm. And thereby, we have a less than or equal to symbol here. Now, is this an estimate that we want? Well, if you recall, estimate means we don't want the right-hand side to involve any variable or unknown. Okay, it should be a constant, and that constant should be known to us. Now you see, this is known to us, provided if we know f double dash maximum norm, assuming that we know this part, but still this part, although it's known for a given x, but it involves this variable x, right? Therefore, still I don't prefer to call this right hand side as an estimate for this. I want to freeze this x also. So what you do is you try to find the maximum of this function and then again replace that here, and that will actually fix this term also. That is the idea. Now, what is the maximum of this function? That is, consider this term as a function, say g of x, right? You can see that the maximum of this function is attained at the point x equal to x naught plus x1 by 2. You know how to find maximum of a function. You can check that. So you put x equal to x naught plus x1 by 2. Thereby, you can see that mod x minus x naught into x minus x1 is always less than or equal to x1 minus x naught square by 4, right? So this holds for all x in the interval x naught to x1, right? Because we are confined only to this interval as far as this function is concerned, right? Now you put this into this, you can see that this is further less than or equal to, I'm just dominating this term by this, therefore I will have x1 minus x naught the whole square by 4 into this one, f double dash infinity comma I divided by 2. So that gives me this as an upper bound. You can see that there is no x involved in it, as well as there is no unknown involved in it like xi of x, right? So you can see that the mathematical error involved in P1 of x when compared to f of x is less than or equal to this, irrespective to whatever x that you choose in the interval x0 to x1. So in this interval, we have this estimate for our mathematical error. Now you can see that this is true for all x in this interval. Therefore, even you can take the maximum norm for this function and conclude that the maximum error will, we may say that this is x0 to x1 is less than or equal to x1 minus x0 the whole square into maximum norm of f double dash divided by 8. Well, in particular, we can take x0 equal to A and x1 equal to B because the choice of nodes are in our hand. Therefore, if we choose our nodes like this, then in fact, we can achieve this estimate on the entire interval AB. Let us be more precise and take the function f of x to be sin x, an easy function to handle. And let us try to approximate this function sin x by the interpolating polynomial of degree 9 by giving 10 node points in the interval 0 to 1 and the corresponding function values at these nodes. Now, our question is, how well does this polynomial approximate the function sin x? From our theorem, we can see that the mathematical error involved in P9 of x when compared to the sin x is given by the 10th derivative of f evaluated at some unknown point xi x divided by 10 factorial into the product of x minus xi, where I ranges from 0 to 9. Right? Now, in order to get an estimate for the mathematical error, let us first take modulus on both sides, and you write this as 1 by 10 factorial times mod f10 of xi x, which is sin xi x, right, into pi I is equal to 0 to 9 mod x minus xi. Now you can see that whatever may be this psi x, we know that mod sin is going to be less than or equal to 1. Therefore, we can write this as less than or equal to 1 by 10 factorial into pi I is equal to 0 to 9 mod x minus xi. Well, now we have to dominate this term also. in the last example, it was a quadratic polynomial, so we could easily find the maximum of this term. But here it happens to be a 10th order polynomial. It sounds not so easy to find the maximum of this. But however, you can see that x belongs to 0, 1, and also each xi is sitting in 0, 1. Therefore, this term, whatever may be x and xi, their maximum distance will be less than or equal to 1, right? So you can use that fact to dominate this entire term by simply 1 again. Therefore, you can say that this is further less than or equal to 1 by 10 factorial. So that sounds to be an estimate for our mathematical error, and that may be taken to be less than 2.8 into 10 to the power of minus 7, right? Therefore, the mathematical error involved in the 9th order polynomial interpolation of sin x at any node points in the interval 0 to 1 is dominated by this number, right? Again, this holds for all x in 0, 1. Therefore, even this, you can take the infinite norm and write this estimate. And this is finally what is the estimate for the mathematical error. So if I ask you to find the estimate for the mathematical error involved in some polynomial interpolation, you finally have to give an estimate like this, where the right hand side is a known constant, and you should also make this argument, don't leave at this step. I will not accept this. You say that this inequality holds for all x, and therefore it also holds for that x at which this function attains its maximum, right? You write this argument and then conclude that the infinite norm of ME is less than that number. So this step is very important finally. Let us try to get a feeling of this mathematical error graphically. In the first plot, I am showing the graph of the function f of x. In our case, it is sin x in the red solid line. And I am also plotting the interpolating polynomial at various points. To distinguish these two, I am using blue stars to represent the graph of the function P1 of x. Remember, we need two nodes to generate P1 of x. I have taken 0 and 1 as these two nodes to obtain the interpolating polynomial P1 of x. That is evident from the error also. You can see that the mathematical error, in this case, you can explicitly find. We don't need any sophisticated theorem to give the expression, or even you don't need any sophisticated ideas to estimate it. We can just explicitly find it. You can see that the error at these 2 points takes the value 0. That shows that we have chosen these 2 points as the nodes for the polynomial P1. And correspondingly, you can also see that the maximum error, this is your ME1 maximum now, right? In the interval 0, 1, that is around 0.06. Now let me go to increase the nodes and see how the higher degree polynomials approximate sin x. I have taken the quadratic polynomial interpolation for sin x, and again I am representing this quadratic polynomial by blue stars. You can see that it is agreeing with sin x much better than the linear polynomial. Look at the error plot and see what are the nodes that I have chosen for generating P2. The nodes were x0 equal to 0, x1 equal to 0.5, and x2 equal to 1. Coming to the question of the maximum norm of the mathematical error involved in P2, you can see its maximum norm is attained here, and that is something like 7 into 10 to the power of minus 3. Therefore, this is much less than what we obtained from the linear polynomial interpolation. Now I have gone to P9, and you can see that the polynomial is agreeing very well with the sine function. And also you can see that the maximum norm of the mathematical error, which is achieved at this point, and its value is something like 1.7 plus into 10 to the power of minus 12. So it's much less than P2. And you can also see from the error plot what are all the nodes that I have chosen to generate this polynomial P9. The nodes are something like this: x0, x1, x2, x3, x4, x5, x6, x7, x8, and x9. Okay, you can see that theoretically what we obtained as the maximum norm ME9, theoretically we got the result that ME9 will maximum have this value. That is, the worst possible value of this term is going to be 2.8 into 10 to the power of minus 7. That's what it says. And here you can see computationally we precisely got it, which is around 1.7 into 10 to the power of minus 12, which is much less than 2.8 into 10 to the power of minus 7, right? So that is well in agreement with our theoretical result.